Recalling Ohm's law, namely current times resistance equals voltage, it should be stressed that if the voltage is kept constant, any reduction in resistance causes an increase in the amount of current flowing in the circuit, as we've already found out by experiment with a variable resistor. This increase is dissipated by way of heat in the resistive elements. It's easy to understand that it's possible to reach a critical temperature at which the component melts and is destroyed. To avoid this danger, a metal component called a fuse is inserted in circuits. A fuse has a minute, almost non-existent resistance. A fuse is made so that it cannot withstand increases in temperature in excess of 300 degrees, such as that caused by a flow of current greater than the rated value. When inserted in our circuit, a fuse acts as a safety switch. Here you see a circuit prepared for a fuse to be inserted. We see from the ammeter that the circuit is open and no current is flowing. When the fuse is inserted, the circuit is completed and closed, thus allowing electrons to flow. If the flow of current increases, the fuse melts and breaks the circuit. There are different thicknesses of fuse wire in relation to different current-carrying capacities. The function of this piece of equipment, which is inserted in circuits for protective purposes, is obvious, namely to prevent damage to the various components. It's essential to remember that a fuse can only ensure protection if it's of the rated value specified by the vehicle manufacturer. The fuses in a car may be of the conventional type or the latest lamellar ones used on recent production models. These fuses are also marked with a number, 10 amps, 25 amps, etc., and are colored differently for quick identification. Each item of electrical equipment on the car is protected by a fuse. For example, the windscreen wiper motor, the central door locking motor, the window winder motor, and so on. All the fuses are gathered together in a fuse box into which the various supply circuits lead. Each item of electrical equipment on the car is able to operate on the voltage supplied by the 12-volt battery. To illustrate this concept, let's go back to our circuit. If we use the switch to close the circuit, there's a flow of current from the positive pole of the battery to the negative pole via the bulb. On a car, we can do without the negative lead, since the metal shell of the car constitutes an earth via which the circuit is closed. To earth is to put at zero potential. If the earth is oxidized, instead of giving zero potential, it gives a greater value, this value being subtracted from the capacity of the particular item of electrical equipment, which will operate either less efficiently or not at all. It is as if we'd inserted an extra resistor in our circuit. It's very important to remember that if there are variations in the value of the earth, we will not be able to have a stable supply value. A simple test for checking the effectiveness or otherwise of the earth system on a car is to connect our multimeter, positioned with a scale up to 200 ohms, between the negative pole of the battery and the various earth connections on the car. The resistance value measured each time we test should not exceed 0.2 ohms if we're to have a good earth connection at each point. Let's see how to check the voltage supply to a particular item of electrical equipment, the windscreen wiper motor, for instance. We disconnect the connector going from the system to the motor. The first operation is to carry out a check on the efficiency of the earth connection or negative supply by measuring the resistance between the negative pole of the battery and the negative lead of the power supplied to the item of electrical equipment under test. As mentioned already, the value should not exceed 0.2 ohms. To check the positive supply, put the black probe to earth and the red probe on the positive supply lead-in terminal. Using the instrument panel, operate the windscreen wipers. You'll then be able to read off the voltage on the voltmeter. A similar procedure should be adopted, for example, for the central door locking control. You should note that there are two separate circuits, one for opening and one for closing the car doors. If there's current present on one circuit, there cannot be current on the other. The door also houses the circuit for the window winder motor. You can therefore check the presence of a supply of current from the battery referred to earth with the instrument panel on by operating the controls for raising and lowering the window. If there's no supply of current arriving at one of the various items of electrical equipment, we need to go back to the fuse box, identify the relevant fuse, and check whether it's intact. Linked to the concept of earth is that of leakage arising from faulty contacts. This occurs when, with the ignition key off, certain items of electrical equipment tend to run down the battery as if they were still switched on, causing current to circulate in the body shell. So a check needs to be carried out on the leakage of current in the car. This check becomes extremely important on sophisticated cars fitted with electronic devices requiring a constant supply of electricity. To check on the level of current leakage, we use a multimeter as an ammeter, and we connect the plug to A. As you know, the instrument for measuring current intensity has to be connected in series with the circuit. In other words, it should have its black probe connected to the positive pole of the battery and its red probe to the terminal which naturally has to be disconnected from the positive pole of the battery itself. It should be remembered that there are certain electronic devices on our cars which are always supplied with current, and therefore there will always be a reading of a few thousandths of an amp. If there were any leakage in the system, the reading would be decidedly higher. A leakage of 100 milliamps is sufficient to run down a 40 amp hour battery in about 400 hours. But after only 200 hours, the battery would no longer be capable of restarting the engine. If the ammeter shows a high reading, to check whether there's a leak, we need to isolate the individual parts of the electrical system by gradually removing the fuses corresponding to the various items of electrical equipment. Each time a fuse is removed, we continue to check for leakage until we identify the particular item of equipment which is responsible. A concept associated with leakage is a short circuit, which may be defined as a circuit with zero resistance. From Ohm's law, given a constant voltage, if the resistance is close to zero, the current will tend to rise to very high values, greater than those above which the protective fuse will blow. In practice, a short circuit occurs when the positive lead of a particular item of electrical equipment accidentally comes into electrical contact with a negative lead or with the car's earth system. In this case, a large amount of current flows from the positive pole of the battery and is discharged to earth on the bodywork without passing through the switch. The fuse, being subjected to a flow of current in excess of its rated value, overheats and eventually melts and breaks the circuit. On the car, the first thing which needs to be done to identify the section of electrical circuit affected by a short circuit is to isolate all the items of equipment protected by the same fuse by disconnecting the relevant supply leads from the fuse box. We'll use an ohmmeter to carry out the check. One of the instrument's probes should be connected to earth. whilst the other should be connected one by one to the supply leads for the various items of electrical equipment. On the item affected by a short circuit, the instrument will show a resistance reading of 0, 0. Having identified the faulty circuit, we can go on to pinpoint the place where the short circuit was caused. All items of electrical equipment on the car are connected to a single source of energy, namely the battery. These items of electrical equipment, which we consider as resistors, can be connected one to another in two ways, either in series or in parallel. They're series connected if they're connected one after the other. That's to say, the input end of one is connected to the output end of the other. The current flowing through the resistors will be the same for all of them, and the total resistance will be the sum of the individual resistors. When we close the circuit, we can see that current flows. Each resistor will have part of the supply voltage at its ends. Here we've made a series connection in a circuit made out of electrical equipment similar to that found in a car, using electric light bulbs as resistors. Let's connect an ammeter to the circuit for checking purposes. As soon as the circuit is closed, the bulbs light up, indicating that current is flowing, and we can read off the value of this current on the ammeter. If one of the bulbs is removed, or if one of them blows, the entire circuit is then open, and current no longer flows. On the other hand, connecting resistors in parallel means that all the input terminals are connected to each other, and all the output terminals are connected to each other. The supply voltage will be the same for all the resistors, whilst the current flowing through each resistor will be linked to its own value. Usually, the electrical system on our cars is parallel connected with a 12-volt DC supply, as are our homes, even though these have a 240-volt AC supply. Let's now modify our electrical circuit by connecting the electric light bulbs in parallel. When we close the circuits, the lamps light up because current is flowing. Note that if the bulbs used are the same as in the series connected circuit, now that they're parallel connected, they're brighter, since they're both receiving the full battery voltage. We should also note that the current flow is different, as we can see from the ammeter. With parallel connection, removing one electric light bulb does not break the entire circuit, although current consumption is reduced, since it's only flowing in the single remaining resistor. So it's obvious that in a parallel connected system, each item of electrical equipment is supplied at the same voltage level and represents an independent circuit with its own switch. The total resistance of the system, however, will be less than each individual resistor. The current flowing in the resistor causes the loss of a certain amount of energy per unit of time, which is converted into heat. The energy per unit of time is given by the product of voltage multiplied by the current and is called electric power. A distinction should be drawn between two types of power. That part of the energy which is converted into work will give an output, whereas that dispersed in heat will be a potential loss. The unit of electric power is the watt, the symbol for which is capital W. Watts express output. That's to say, the ability to produce work per unit of time on the part of a particular item of equipment. In a starter motor, it will take the form of mechanical energy, whereas in an electric light bulb, it will be luminous energy. In a car, each item of electrical equipment, being parallel connected, is supplied at the same rated battery voltage, and in the event of a malfunction, it has to be checked like an independent circuit. Let's see how the headlamp bulb circuit can be checked after having first made sure that the fuse is intact. After removing the bulb from its socket, the first thing to do is to check that there are no breaks in the bulb filament. The old method of looking at it in bright light in the case of halogen bulbs is no longer relevant. For this purpose, we use an ohmmeter. We connect the black probe to the common terminal of the bulb and the red probe to the terminal of one of the two filaments. As you know, we can tell whether the filament is continuous because this will be shown by a definite resistance reading indicating a closed circuit. If the ohmmeter reads infinity, open circuit, it indicates that there's a break in the bulb circuit. Let's continue our examination of the circuit. Still using an ohmmeter, check the continuity of the earth connection. Connect one probe to the negative pole of the battery and the other probe to the bulb's earth terminal. The ohmmeter should show a reading of not more than 0.2 ohms. Then place the black probe on the multimeter in the voltmeter position. Leave the black probe on the bulb's earth connection and connect the red probe on one of the two supply leads to the bulb. The voltmeter should show a reading of about 12 volts. To continue our check on the electrical circuit, we work our way back along the circuit. First, we check the light switch unit, comprising the group of switches to which the headlamp system is connected. Using a voltmeter, we put the black probe on a reliable earth, and using the red probe, check that there's a supply of current getting through to the light switch unit. Now operate the relevant controls and check whether there's a voltage in the light switch unit's output circuit leads. In both cases, the voltmeter should read about 12 volts. In this way, we've checked the working of the entire circuit, starting from the headlamp bulb and finishing at the supply to the light switch unit. We now go on to check the heated rear window. Both the supply circuit and the earth circuit arrive at the heated rear window. To check that the supply is present, connect one probe of the voltmeter to the input terminal of the circuit and the other to any metal earth on the car. With the instrument panel on, the heated rear window is switched on and the reading on the voltmeter should be that of the battery supply. To measure the total resistance of the heated rear window filament, use a multimeter as an ohmmeter by connecting it between the terminals of the filament itself. The reading should be very close to 1 ohm. Now we can go on to check that there are no breaks in the heated rear window earth circuit. To do this, we put one probe on the input earth to the heated rear window and the other probe on an earth point on the car. The reading should be as close as possible to 0. We now carry out a check to show how the heated rear window's very high resistance value affects the absorption of current. For this check, we use a multimeter combined with an ammeter clamp. Connect the clamp to the supply lead for the heated rear window. Close the electrical circuits and read off the current absorbed on the instruments. In this case, 12 amps. Our experiments show that we can verify the relationship between voltage, resistance, and current and demonstrate the effect of Ohm's law. Sometimes series-connected resistors are used on cars to achieve some measure of control over the supply voltage. One such application of series-connected resistors is the fan in the air conditioning system. When the fan switch is in position 3, the motor receives its supply at the rated battery voltage and turns at maximum speed. When the switch is moved to position 2, the internal contacts change and one of the two resistors is switched on, reducing the voltage and therefore the speed of the motor. Finally, when the switch is moved to position 1, both resistors are switched on, causing a further drop in the voltage supplied to the fan's motor. Variable resistors are also used on cars, as for example the rheostat for the instrument panel lights. The variable resistor is achieved by a cursor which runs on a resistor. Depending on the position which it assumes, the resistor is completely or partially turned on or off, thereby varying its value. And that's the end of Module 2 in this 4-part program.